everyone. Welcome to the Locomotion session. There was another Locomotion session earlier this morning together with some 3D UI papers. So technically this is the second Locomotion session. So we have 4 excellent talks. You know by now that everybody gets 12 minutes and then 3 minutes of questions. So please prepare your questions. We're looking forward to hearing your questions. The first talk, none of the authors could make it, but Ke Zhou from the same institution from Southeast University in Nanjing, China, was able to be here and present the paper. This is also to say that he will not be taking any questions since this is not his work, but you can always scan that QR code and ask questions directly to the authors. So please go ahead, Carl.
So good afternoon, everyone. So yes, the authors of this paper cannot attend ISMAR due to the visa issue, so I will present work instead. And the authors make a QR code here, and at every presentation, at every page, you can just scan the QR code and ask questions to the authors, and the authors are online, ready to answer questions. So the name of this paper is My Go, Virtual Reality Locomotion Prediction using Multitask Learning. So locomotion is one of the fundamental interactions in VR. It defines how users move around in virtual environments in a continuous and immersive way with a high degree of freedom. However, as we know, existing locomotion methods still face a number of challenges. For instance, on redirected work, we apply redefined optimization algorithms to reduce the working distance and avoid collision risks, but it will still need a certain amount of physical space to ensure safety. On the other hand, those standalone methods like joystick-based locomotion or working place, researchers usually define artificial mappings to translate specific actions into virtual steps. But these mappings can sometimes feel unnatural, thus creating extra cognitive load or conflicts, especially when users are performing multiple tasks or interactions. And some of them also rely on extra devices like sensors and cameras. So to draw on the strengths to offset the weakness, in our work, we propose a locomotion prediction method called MyGo. The key idea is to extract working intention from subtle body movements. Importantly, our method only uses data that can be collected from a head-mounted display, and we train a deep learning model using multitask learning. This allows us to accurately predict users' future trajectories while they work in the virtual environment with current locomotion methods. Our motivation is inspired by a classic text from ancient China, Xiao Yao You. In this text, there is a fantasy creature called Kunpeng, which soars freely across the ocean and the sky. The original text is very hard to understand, so we highlight the main text here. The author said that it is the vast depths of the water and air that enable this long journey. By analogy, we believe that a free and unfettered experience in VR also requires powerful and intelligent locomotion methods. Now, going back to challenges we mentioned at the beginning, to identify the bottleneck, we rethink the procedure of how we perform a walking action in VR. It can be divided into 3 processes. First, perceiving the outer stimuli. Second, conveying our intention of walking, either explicitly or implicitly. Last, performing the action. In this loop, locomotion essentially acts as the translator between human perception and action. Based on existing evidence on the correlation between behavioral intention and action, and inspired by prior AI studies on motion patterns, we insert the AI model in this loop to serve as the decision-making tool for VR walking interactions and replace the translation process by modeling available human parameters like history, trajectories, and gait steps. It helps us to achieve the locomotion that eliminates dependencies on peripherals and simplifies the translation process. To achieve this, we construct a data set. 3 popular standalone locomotion methods and 3 different virtual environments are involved in our experiment. These 3 things have different fields of view to encourage users' different behavior, especially their gaze behavior. We totally recruited 15 participants who were asked to complete object finding tasks. The blue landmark would be collected when approached and would reappear in another location randomly after that. This slide shows some detail about the dataset acquisition. We assign the order of virtual environments and interactions in a Latin square design. We follow the established method and collect features summarized in this table, which includes the movements both in physical and virtual world, as well as the gaze data. Additionally, we also collect the walking intention as a label feature by indicating values from Locomotion, like the touchback button and amplitude of arm swing. For model training, we build our architecture shown here. The input data are first encoded using a bidirectional LSTM and transformer. Then we perform multitask optimization between the walking intention classification and trajectory regression. In particular, the model receives samples with a window length of 60 frames and predicts the coordinates of the 5th frame after last input frame. Losses from 2 branches are updated, balanced with a learnable parameter. Here are the evaluation results and ablation studies. It could be observed that the proposed model consistently outperforms the baselines across all data sources. Additionally, when we extend the prediction horizon to match the baseline setting, the performance remains stable. This slide shows the result of the ablation studies on the multitask learning module. The introduction of the walking intention label is also positive for improving the accuracy of the baseline. It demonstrates the individual contribution of the proposed training strategy. Here is a comparison of different temporal embedding architecture. To validate the effectiveness of our compound structure, we construct 2 additional models with pure transformer and LSTM architectures. The result also shows the superiority of the proposed model. And this graph shows how gaze data contribute to performance in different scenarios. We find a similar conclusion to the establishing research that the gaze behavior is beneficial for the predictive models. Except for offline evaluation, we also implemented a real-time prediction framework to support a user study. With the help of a model deployment plugin, we ensure the response speed is fast enough to output predictions before the target frame arrives. We totally recruited 12 participants for free exploration tasks. The result in this table showed that our model performs well in practice. And here are some visualizations. The green curve is the prediction from the proposed model. It's exhibits a closer alignment to the orange ground truth, especially during sudden direction changes. You can refer to these red arrows and rectangles, which indicates those significant differences. However, we acknowledge that there are still limitations. For example, we only test a real-time user study on one single combination. Therefore, a comprehensive evaluation would be necessary to verify generalization. Also, the performance degradation in the real-time study indicate that further optimization of the data and model architecture is required. And that's all for this paper. Thank you for your attention. And if you have any questions or suggestions, you can just scan the QR code and ask the authors. And authors are online ready for your questions. Thank you.
Hello, everyone. My name is Sungwoo Eun. Today, I'll be presenting our work on how the location and speed of peripheral optical flow affects unintended positional drift, or UPD, during walk-in-place in VR. So, in VR, navigation is critical for immersive experiences. There are 2 major types of navigation techniques. The first is teleportation-based movement, which is fast but disembodied, as shown in this video on the left. The second is gesture-based movement, such as walk-in-place, which preserves natural motion cues with an embodiment. In WIP, users move forward virtually by stepping in place without actual physical transition. Because of this, users often fail to notice gradual positional drift that accumulates over time. For example, if you see the video on the left, even when the participant believes that they are walking perfectly in place, gradual positional drift accumulates. This drift could be caused by physical imbalance, inconsistent rhythm, or variation in step force, which all leads to asymmetric motion interpretation. And importantly, UPD is not just a minor inconvenience. It is a safety critical factor. For instance, if someone drifts into an obstacle in a physical environment, like if you see the person hitting the cone, it can cause serious problems and is a very critical, safety critical design factor. Previous studies have attempted to address UPD using haptic feedback, auditory cues, or passive constraints. For example, if you see at the top, Nielsen provided extra visual or auditory cues when participants drifted too much during WIP. He used stop signs or auditory feedback when UPD occurred too much. Disney's Holotile also works in this way, correcting movement after drift occurs rather than preventing it from start. However, most of these are post-hoc correction strategies. They detect drift only after it has occurred. So, in our work, we wanted to take a different perspective. Instead of treating UPD as something to be corrected after it happens, we asked a more fundamental question. What actually caused UPD in the first place? Specifically, we focused on visual stimuli, which is optical flow, and examined how astrometries in visual motion might influence UPD. For example, imagine a pedestrian walking along a street. On the left side, there's a static wall, which produces sparse optical flow. On the right side, there's a busy road with moving vehicles, which generates dense optical flow. These astronomic visual motions can cause a sense of viction, with my subtly distribute postural balance. We believe that this imbalance could be a key underlying mechanism of UPD. To test this idea, we specifically focused on peripheral optical flow and various location, left, right, or both sides, and its speed to see if whether these visual astrometries constantly influence UPD. To test our theory, we accumulated two research questions. The first research question is how does the speed of peripheral optical flow influences the magnitude of UPD? So we tested slow speeds, as you see at the left, and fast speeds, as you saw at the right. The second research question is the relationship between the location of peripheral optical flow and the actual direction of the user's drift. For this, we modulated peripheral optical flow directions in the left, the bilateral, and the right specifically. To answer these questions, we used the 2x3 within subject's design. The independent variables were optical flow speed, which we made 1 minute per second or 2 minutes per second, and location, which is left or right or both. 27 participants took part, including 12 male and 15 female, with a mean age from about 24.7 years. And the virtual environment was a long tunnel-like corridor with checkerboard walls designed to create strong optical flow. We collected both object and subjective measures. For the objective measures, we used the trajectory tracking with the MetaQuest 3 headset. On the right, you can see a top-down view of a random participant's trajectory. The yellow dot indicates the participant's starting position in the real world. We measured two types of movements: lateral movement, which is the participant's left or right movement along the x-axis. And we also measured the forward-backward movement along the y-axis, which is the front-behind movement. And to ensure consistency across participants, we normalized all trials to 100 steps per participant. This allowed us to compare movement patterns under equal conditions. For the subjective measures, we administered the simulator sickness question, or the so-called SSQ, and the lateral performance inventory, which is further evaluated with the Miles test. The Miles test assessed eye dominance. Participants extended their arms forward and formed a small triangle with the hands, like hands something like that. And they formed a small triangle to frame a distant object. For instance, you can see that the person extended their arms to see an apple. Then, they closed each eye alternately, and the eye that keeps the object centered in the triangle is identified as the dominant eye. So, If you see that the person, if the person closes their left eye, you can see that the apple comes into the hand, which is covered. And if you see that the person closes their right eye, you can see the apple is still centered. So the person is left eye dominant. And the same is from, and the opposite is from the right eye dominant. The procedure was as follows. First, participants first completed a pre-questionnaire about their rear experience and eye-hand log dominance. Next, they went through a training session to get comfortable with WIP. We then ran one baseline trial with no optical flow, followed by the 6 experimental conditions, randomized using a balanced Latin square. And whenever a trial ended, we quickly positioned a wheeled chair behind them and instructed them to close their eyes and sit in order to guide them to the questionnaire station. This procedure minimized the possibility that the participants might unconsciously attempt to fight the drift if they became aware of their displacement or across the trials. After each condition, participants rested for 1 minute and filled out the SSQ. So, in total, participants completed 7 trials, 1 baseline plus 6 experimental conditions. Our hypothesis was derived from the research questions. The first hypothesis is that the magnitude of the UPD in the forward direction will increase proportionally with the strength of the vection. The reasoning behind this is that faster optical flow should induce stronger vection, which should create more imbalance, which should create greater sensory imbalance, and in turn lead to larger forward drift, or UPD. In other words, as the speed of visual motion increases, we expected stronger vection and more pronounced UPD. Our second hypothesis was that the direction of lateral UPD would be opposite to the direction of the vection stimulus. For example, when driving or walking along a curved road turning to the right, we naturally perceive more optical flow from the left side, which is highlighted yellow, of our visual field, than the right side, which is highlighted green. This stronger left side motion can induce the sense of vection toward that side, causing the body to subtly lead or drift in the opposite direction, which in this case would be to the right. Similarly, in our experiment, we expected that when optical flow was presented on one side of the wall, participants would trend to drift toward the opposite side as a compensatory response to the asymmetric visual input. So, results. We expected stronger optical flow, specifically faster speed, to increase during forward drift. This was partially supported. In the bilateral condition, faster flow produced more drift, but in the left and right conditions, results were inconsistent. This suggests that asymmetric optical flow may introduce sensory conflicts that disrupt the expected effect. We also hypothesized that drift direction would be opposite from the vection stimulus. For example, left flow would cause rightward drift. This was not supported. Instead, asymmetric conditions actually suppressed drift, producing smaller magnitudes overall. This indicates that multisensory integration and attentional control could play a key role in moderating UPD rather than simple reflexive responses to visual flow. We further expected stronger optical flow to increase cyber sicknesses, but SSQ scores remained constantly low across all conditions. This shows that optical flow manipulations did not increase VR sickness in our study. One particularly interesting finding was the effect of eye dominance. Right eye dominant participants constantly drifted left, while left eye dominant participants drifted right. This suggests that individual perceptual traits could meaningfully moderate locomotion behavior in VR, and that eye dominance should be considered in VR locomotion design. Of course, there are limitations. Our participant pool was imbalanced in terms of eye dominance. Only 17% of the participants have left dominant eyes, and that limited the general of the observed lateral drift tendencies. Future work should balance the participants of the left-right eye dominance. Also, there were low SSS scores throughout the experiment. This conflicts with prior studies, which had higher SSQ scores when higher vection was induced. However, this could be because our experiment only had straight routes throughout the experiment. Future work should focus if curves or long-time WIP could induce VR sickness more often. To wrap things up, we explored how the location and speed of peripheral optical flow relate to UPD in WIP. We found that asymmetric optical flow surprisingly suppressed UPD compared to symmetric flow. However, no clear effect of speed was observed. We also found that direction of UPD seemed to vary with the dominant eye. However, further research is needed for more confirmation. So, we suggest that UPD could emerge not merely as a visual artifact, but from multisensory integration and attentional control. This is the end of my presentation. More details and references are in the paper. I'm looking forward for your questions and comments. Thank you for listening.
Questions from the audience? Yes? There is a, in the front row. Thank you.
Thank you. Thank you for the great presentation.
There are more seats on that side of the room if you guys want it.
So I think this is a really interesting study about why UPD occurs, like what affects UPD.
Yep.
I was just wondering if like any of the results you discovered could kind of be used to prevent or maybe kind of direct UPD in the opposite way. So like the person returns to the original position, like for example, like apply optical flow to the opposite direction or like an opposite size. So could these results kind of be used to improve upon the UPD problem?
Yeah, that actually should be a fundamental goal from every UPD. So for instance, if the results from our study tended to be something like if we induced optical flow in one direction, a tendency is kind of like constant, then we could use this results to kind of suppress UPD and make somebody go back to their first state without somebody noticing. But since the results kind of tend to say that UPD could actually be a little more difficult or have a more multisensory conflict than most users, so I think that we need a little bit more studies to identify what causes UPD in the first place.
Another question? Yeah, I'll ask a quick question. So, do you think that there is a way of directing the user by introducing some sort of redirection into the visualization to steer the user back towards the same physical position, since the headset is tracking with respect to the physical world? So the headset would know where that intended stationary location would be.
Can you say it from the headset again? I kind of lost it.
Do you think there is a way of modifying the visuals through redirection such that the user basically steers back towards that original position?
Oh yeah, that could be possible. So the experiment that we did was actually kind of extreme, with extreme environment, which had only one side with optical flow, which is very dense, and one side with no optical flow. But if we kind of mixture the optical flow together to induce some kind of pattern, so that could be possible.
Any other question? Yes, at the back. We're getting the mic there. Thank you.
I really wish your hypothesis was correct. Thank you for reporting out the negative result as well. I was wondering, for instance, my shoes, if I wear it after a few years, if you look at the back of the shoes, one side of the shoes, like a right side of the shoes always is more damaged compared with the other one. So I was wondering, because of that, like a tendency of how you work in general already affected their shoes or some effect, and then if you can reverse it, like ask them to wear the new shoes so that you don't really have the differences on the shoes and so on, or like an intervention on the height of the shoes can potentially adjust the tendency of drifting.
Yes, that is actually an interesting point. So the floor that we did to experience was actually a quite solid floor without something slippery or no kind of rocks, just a smooth floor. So that could be one if not many reasons that UPD could actually be caused in the first place. So actually, if we tried to make the experiment much more precise, then we should have made all the participants wear the same kind of shoes or something like that. So that could actually be a great point for future studies.
Let's thank the speaker again. Thank you.
Thank you.
Thank you. So the third talk is exploring plausible preference of body-centric locomotion with reinforcement learning in virtual reality. The team is from several universities, Jinan, La Trobe, and the Hong Kong Polytechnic. And the talk will be given by Zichun Mai. Please go ahead.
Good afternoon, everyone. It's a great pleasure to be here at ISMAR. I'm Zijun Mai. Today, I will present our work on exploring possible preference of body-centered locomotion with reinforcement learning in virtual reality. Virtual locomotion is a fundamental interaction task in VR, which aids to simulate real-world working within virtual environment. It can be found in a number of VR applications, such as VR games, simulation training, and virtual navigation. A key criteria for virtual locomotion is plausibility, which refers to the illusions of actually working in VR. It is closely related to presence or immersion. However, achieving a plausible locomotion experiment traditionally relies on advanced but expensive tracking device and require large physical space for one-to-one mapping, which are not acceptable for most consumers. Body-centered locomotion offers a cost-efficient alternative with consumer-grade devices such as VR headsets and controllers. Such locomotion allows users to control their viewpoint movement in VR through self-movement, such as arm swinging or head tilting, which can enhance the working illusion. Additionally, it is feasible and can be used in limited physical space. However, a lack of research explores possible preference for body-centered locomotion, making it unknown which configuration achieve higher plausibility in VR. To address this problem, our study aims to examine users' preference to identify the most possible configurations. There are two main challenges. First, designing such locomotion is complex, which involves multiple factors such as point of view transfer function and body parts in sitting and standing posture. Different combination of factors and posture could lead to varying levels of plausibility. Second, existing evaluation methods have limitations in quickly and intelligently gaining possible preference for body-centered locomotion. For example, questionnaire or interviews are time-consuming, while suggestive matching requires prior knowledge such as priority for factors level is based on previous studies. To respond to these challenges, we propose using reinforcement learning to evaluate possible preference for body-centered locomotion. We decided an RL agents to learn users' interaction behavior and annotate their preference for different factors in sitting and standing postures. We implemented the agent using the Q-learning algorithm. To evaluate possible preference of body-centered locomotion, we first constructed a 32 by 5 Q table to store the expected rewards for changing each factor's level in all locomotion configurations. The agent's main tasks are to identify the factors with the highest rewards and suggest changing its levels, such as switching the point of view into the first-person perspective. Users then tried the configuration and decided to accept or reject the modification. Based on their feedback, the agent measures the rewards and updates the Q table using the equation shown in the figure. Finally, it gradually gains possibility. We conducted a within-subject experiment to evaluate possible preference using the decided RL agent. For sitting and standing posture, we consider 5 factors, including the point of view, auditory feedback, body part transfer function, and its coefficients. Each factor has 2 levels. Our key evaluation measures include RL score, rejection rate, number of visits, and convergence. The experimental procedure is shown in the video. In each trial, the IL agent presents a locomotion configuration, shown with a yellow button, and a suggested modification highlighted in green. Participants could switch between factors, levels, and task configuration by clicking the trial button. During the locomotion task, they pressed the triggers to start moving along a bridge and could exit any time. Once they determine on their preferred level, they confirm their choice with the confirm button. The table shows the top 5 configurations for possible preference of body-centered locomotion. There are 3 main findings in our study. First, users prefer using arm swinging in the standing posture because it is similar to everyday working and can enhance immersion. In contrast, they prefer to use head-based locomotion while sitting because such small movements were easier to perform in this posture. Second, all participants prefer the first-person perspective in the standing posture, which can enhance the sense of embodiment. However, in sitting, a notable number of participants prefer the third-person perspective because this posture conflicts with an obvious working avatar. Third, for the other 3 factors, preferences were constant across both postures. Users show a clear preference for environmental sound and a linear transfer function with a coefficient of 3, which can enhance the present and overall locomotion experience. To validate the effectiveness of RL agent, we use Bayesian methods to assess posterior possibility for choosing different configurations. In addition, we use a post-experiment questionnaire to investigate the possible preference for each factor. The results show that the possible preference attained by RL agents align with those using other methods. However, compared to previous work without an RL agent, such as the suggestive matching method. Our study can intelligently evaluate possible preference without previous knowledge and quickly determine their preference within 15 trials, in total 32 configurations. Our research can guide the design for creating our possible locomotion experiments. For standing, we recommend using the arms ringing methods to simulate wheel working, which is suitable for ground-based locomotion. For sitting scenarios, like flying or VR flying, head tilt-based control is an efficient alternative. In addition, some users prefer the third-person perspective while sitting. This finding suggests design implications for VR psychotherapies to create third-person memory and prolong VR navigations to improve spatial orientation in this posture. Our study have two main limitations. First, lack of control without RL agents for comparison. Second, neglect participants who only provide preference ratings. In the future, we plan to address both issues. In addition, we will study possible preference on curve movements using other locomotion methods, such as redirection working, as well as incorporate additionally flatter night studio visions with other algorithms. That's all. Thank you for your attention.
Thank you. Let's see if there are any questions. While you're thinking of your questions and what to ask, I'm going to ask you a quick question. It seems like you had a very long and relatively narrow path, and maybe the participants were trying hard to stay on the bridge. Was there just a fixed translation, or was there any possibility of turning left and right, and did they have to stay on a straight line?
Yes, participants in our experience only walk on the straight line.
So they were fixed on that straight line?
Yes, it's
okay,
fixed
so my
on the
follow-up
straight
question
line.
is, do you think the results might change if they somehow have to be careful to stay on a straight line? Do you think that the results might be different?
Yes, it's a great question. When participants walk on the curved line, their possible preference may affect by the direction and other factors. We will incorporate this factor in the future.
Any questions from the audience? Another quick clarification. When you say third person, was the view advancing with the participant? I think I missed that, or maybe it was in one of the videos. Like, when you saw the participant from the back, was the view points staying at the fixed location with respect to the participant? With respect to the avatar?
I'm sorry.
It's just a detail. Like, I'm not quite sure how the view was following the avatar. Like, was it at a fixed location behind the?
It's a fixed location behind the avatar.
But constant location with respect to the avatar,
yes.
correct? Okay.
Yes.
Any questions from anyone? Anything else? Well, if not, let's thank the speaker and let's get great. So here's the last talk of the session. The title is Investigating the Effect of Visual Cue Density on Situational Awareness During Immersive Navigation. And the team is from several places, including Graz University, University of South Australia, and the No Center Research, GmbH. And the talk will be given by Nicole Weidinga.
Thanks. So hello everyone, my name is Nicole. I'm from the No Center in Graz, Austria. And I will present to you our work, also on behalf of my co-worker, so Neven is here. Our work where we investigated the effect of visual cue density on situational awareness during immersive navigation. And in the past, a lot of different navigation guidance queues have been explored and developed. So here I have some examples. And they all have like different characteristics and are suitable for different kind of scenarios. And I included work from AR and VR literature, so some concepts you can find in both fields. And in the past, researchers have started to also look beyond performance metrics, so not only like how quickly can this queue guide me to my desired location or find the right object. They also investigated that if these queues can have other like perceptual or cognitive effects, like effects on mental load, spatial memory, or sense of immersion. And it is acknowledged that persistent queues, so not only navigation and guidance queues, but in general, can have negative effects. So they can lead to visual clutter, distraction, or spatial disorientation. And here I have an example. So in this paper, they had this adaptive system. So they showed this path-based queue, and whenever the system detected a possible dangerous area, they were hiding the queue completely. And that's where we had the question or the idea if already more subtle changes in the queue design, like in this case queue density, can have an effect on situational awareness. But we were not only interested in the impact on situational awareness, we also wanted to still look at the performance, the task performance, and also at the user experience, so how this queue density affects all of these three things. And when I speak of queue density, I mean the spatial frequency. So here you can see the three queues that we compared, from highest density to lowest density. So the first one is the path line. It's a continuous line on the path. The arrow trail shows some arrowheads at certain intervals on the path. And the last one only shows arrows at the corners, so whenever the user needs to change direction. And we conducted our study in a virtual reality environment. So we had this 3D scanned floor from our building, and you can see it's quite big. So here on the left you can see the floor plan, and it had more than 1,000 square meters. And the machines, they don't belong to the scan. We added them, but more to it later. And to enable locomotion, we used omnidirectional treadmill, the OmniDeck, which allows the user to walk freely in the environment without being tied to any kind of strings. So I hope you can see here on the right how it works. And what do the machines do now? So we added them to create our tasks. So we had two tasks. The main task was for the user to fix machines. So the queues would lead them to one machine at a time. They had to fix it, and then the queues would lead them to the next machine. And they could very easily be fixed. So you can see here there was a red light indicating that the machine is broken, and then they just had to adjust the lever and fix the machine and make it happy again. And our second task was to assess the situational awareness. So we asked the users to report anomalies, and we had 3 different types. So puddles, then abnormal looking machines, and these loose cables. And we had 6 per type in each path, so 18 in total. I forgot to mention, they also had to fix 18 machines. So the path then in total would cover around 400 meters in total distance. And we also asked them to focus on their main task so that they don't go around in the scene and look for the anomalies specifically. And we had 24 participants for our study. They experienced all 3 queues, so we had a within subject design, and of course we counterbalanced the order of the queues, and we had breaks in between. But before the study started, we had an extensive training with the participants, not only to get them used to the interactions and the tasks, but also to make them used to the OmniDeck. So we really took our time with that to also set up all the speed for the treadmill and so on. And in the end, we also gathered their end feedback after they experienced all 3 queues. And regarding performance, we didn't see any significant differences, which was surprising for us. So, for example, we expected that they would have a higher distance traveled or more time needed for the path line. We assumed they would just follow the path more strictly than with the other queues, which was not the case. And this could also be due to our layout or of like the floor plan of the building and also our path design. So yeah, with a different layout it might look different. And to assess situational awareness, we looked at the performance metrics of the second task. For example, we looked at reaction times, so how long it took them from first seeing the anomaly to actually reporting it. And here we saw that the medium density queue, the arrow trail, was significantly better than the other 2. And we also looked at how at the anomaly reports in general, how many they reported, if they found them all. And here we didn't find any significant differences. But during the study we saw that the puddles were a little harder to detect for the participants, so that is why we also looked at these results separately. And here we saw that for the highest density queue, the path line, the results were significantly worse than for the other 2. So overall, the arrow trail had here the best results, so it seems that it had a nice balance of giving them enough navigational support so they don't have to look for the queues, but still being less visually intrusive than the path line. Results for user experience were also significant. So we had 2 customized questionnaires where we asked them for their perceived support and the ease of use for each queue. And here the path line and arrow trail had similar good results. The turn marker, so the last queue, was not really popular among participants, but we expected that because it's a little harder to understand than the other 2. And similar, the results for the NASA, where the turn marker had worse results than the other ones. And in the end, we also asked them for their preferences. And it's interesting to see here, I think, that the users acknowledged that the highest density queue was most helpful and the easiest or the least effort to understand. But in the end, they still preferred the medium density queue, the arrow trail. And I think this is also reflected in the results for situational awareness. And they stated that it gave them enough navigational support without being too intrusive. So they preferred this combination. So overall, to summarize the results, the arrow trail is, so we can say that the winner. It had the best results overall. It had best results for situational awareness and was also preferred by the user. And in general, we could show that variations in queue design can influence situational awareness and user experience without compromising the task performance. But again, maybe in a different setting, this could look differently. And we also saw that moderate changes can have a positive effect, while more drastic changes might not lead to the desired effect, and this should be considered when designing this kind of queues. And regarding future work, so for now we just looked at the queue density as in like spatial frequency, but of course you could also vary it in other ways like transparency or line thickness, and we also just considered visual cues, but of course there are also like haptic or auditory cues that you could use. Also, we think we could extend or use more different kinds of anomalies. So we only used static ones, but it could be interesting to have some animated anomalies. Also, results might change according to the user experience. So in our case, they all had the same kind of experience level, but some users that are used to the scenario or the task might prefer other cues than less experienced people. But most importantly, I want to point out like the last point on this slide, we conducted our study in a VR scenario, but it would be also interesting to see the results in an AR scenario, especially because here this topic of situational awareness is more important, as it's actually a safety concern when you walk in a real life environment. Right, thank you very much for your attention, and looking forward to your questions.
Thank you. Questions from the audience? Yes?
Yeah, hello. Actually, you were saying that you performed some training before the task was performed, right?
Yeah.
And so did you consider, because if when you have already trained the person who is to be performing this task, and then you're giving this 3 kind of cues, so because the person is already trained with the kind of scenario, that's why the difference in the performance is not visible. Did you try somebody who is not trained and then asked the...
So in the training, we didn't give them like the task. So we just showed them how to fix a machine and how to report. But the most important thing was to get them used to the OmniDeck.
Mm-hmm.
Because you also, for the OmniDeck, you can, for example, set the speed, and we wanted to have the speed constant throughout the conditions.
Mm-hmm.
And so that is why we really had to train them to get used to the OmniDeck, not that they like increase the speed and then maybe, walk out of the OmniDeck because they, are more experienced. But regarding the task, maybe not related to the training, but in general, if you have a more complex task, it could also be a different or more significant result.
Yeah.
I hope that
Yeah,
answered
yeah,
it.
yeah. Thank you so
There is a question. Yeah, right there. There you go.
Okay. Yeah, thanks for the very interesting presentation. So I have 2 questions about the study. So first, there's in this study it is observed that there is no impact, or maybe I think a very small impact on the completion time. I would say from the queue. Is it possible that with a different task, because right now this task take a long time to finish, so the time the user used to find the queue or maybe process the queue is, I would say, relatively small compared to the task time. So if we have a task like a task shorter, is it possible that maybe you will see some significant difference? And the second question about is some insight about the queues, or maybe I think you have some insight about queue. Is it possible that it is not the density of the queues matters? Is it possible it is the type of information that the queues provide to the user matters? Because when it is low density, technically speaking, the user need to calculate the path from the user to the queue by themselves. But if that is a high density, in fact, there is a path. They simply can follow that. So it is direction versus path? Is it possible that is the case?
Okay, so I hope I remember now your first question correctly. Was it if the task would be more complex,
If that is, I would say, simpler.
if it would be simpler?
Yeah, for example, like right now, I can imagine like it might take 10 seconds to walk from one machine to another machine.
Yeah.
But if that is just like, for example, the user only need to find something, is it possible in that case, the queue can make a difference?
So the task in terms of like just walking, so we actually did it on purpose that we had this larger scale environment, because I think if, for example, you just look for something in the room, like a path-based queue might not be the thing that you want, maybe a different kind of queue. And it was the same like for everyone, like the walking, so I think that we chose this kind of task did not have an impact, or at least not that much. I really think it is more the layout that didn't allow much freedom in walking from like one part to the other. So we had this like huge hallway that, yeah, they could just walk straight, for example. Maybe if you have more like open areas, maybe then you would see more differences, I think. And the second question was, the type of queue. So we actually, they're all three path-based. So all these queues are shown on the path, just not. So the line is highlighting like the whole path, while here in the video it shows these arrowheads on the path. And the other one, like the last one, only at the corners. I was wondering if maybe if the user like a design of a queue, if then it would also be better. So a lot of people said that really liked the design of the second one. So it said they told me it looked like visually like appealing. So maybe that could have also an influence.
Gotcha. Yeah. The reason I asked this question is because one of the authors I would say of this paper, he also published on another button pressing task. It's also line versus arrowhead, and I think I would say potentially different tasks, but I think maybe you can compare results to that one.
Yeah. Sorry, I'm.
Yeah, I just mean I think one of the authors in this paper also published another paper on button pressing task, also arrowhead versus a line. So maybe but different task, but the results very different.
Oh, okay. But was the arrowhead like also in the path, or like was the pointing arrow?
From the source, I think I would say point to.
Okay. Yeah. Then.
Okay. Any other question about this paper? If not, let's thank Nicole, and let's thank all the speakers for an excellent session.